Hi, my name is Andrew Kaz, and I'm speaking to you today from the Fred Hutchinson Cancer Research Center in Seattle, Washington. And I'm also affiliated with the University of Washington School of Medicine in Seattle. And I'd like to thank the organizers of DDW for giving me the opportunity to present my research abstract in this video. The title of our research is Unique Methylation Signatures and Molecular Subclasses in Barrett's Esophagus and Esophageal Adenocarcinoma revealed by methylation array analysis. And my co-authors are Xiaozhen Wang, Jeffrey Virgin, Kay Washington, Ron Liedner, Amitabh Chak, and William Grady. And our reasons for undertaking this study were to gain a further understanding of the methylation patterns in the squamous esophagus, Barrett's esophagus, Barrett's with dysplasia, and esophageal adenocarcinoma. Also to explore the idea of a high and low methylator phenotype in Barrett's and adenocarcinoma, and determine whether there are differentially methylated genes that will segregate these subclasses. We know that individuals with Barrett's esophagus are at increased risk for adenocarcinoma of the esophagus, which is highly increasing in Western countries. And those with Barrett's esophagus are therefore typically enrolled in endoscopic surveillance programs, despite the fact that most will never progress to cancer. Many groups, including ours, are therefore searching for biomarkers that will allow us to better risk stratify those patients with Barrett's who are at greatest risk for progressing to cancer. And one type of biomarker we've been looking at are epigenetic changes in the form of DNA hypermethylation. We've used the Golden Gate microarray array from Illumina to evaluate the different tissues from squamous to Barrett's to high-grade dysplasia and cancer. The Golden Gate array has 1,500 approximately CpG dinucleotides, representing over 800 cancer-related genes. And on this array, we've had 29 normal squamous cases, 28 Barrett's cases, 7 Barrett's with high-grade dysplasia, and 30 adenocarcinoma cases. And we've been analyzing the results from these studies in several ways. First, when we combine together all the squamous cases, Barrett's cases, dysplasia cases, and adenocarcinoma cases separately, and we look at methylation as a median across all 1,505 CpG dinucleotides, we see an increase in methylation from squamous cases, which have very low methylation, to Barrett's cases, which are more intermediate, and then higher methylation in the dysplasia and cancer cases. When we do unsupervised hierarchical clustering of the cases, we find distinct methylation signatures that discriminate the squamous cases versus Barrett's, squamous versus dysplasia, and squamous versus cancer. We also performed differential methylation analysis to identify those CpG dinucleotides that exhibited statistically different methylation between the groups. One example is we found 337 CpG dinucleotides that distinguish the cancer cases from the squamous cases. We were then interested in looking for subgroups within the Barrett's cases, or subgroups within the cancer cases. We know that in other cancers, for example, breast cancer and colon cancer, that there are high and low methylator subgroups. The CIMP, or CpG island methylator phenotype cancers in colorectal cancer, are one example of this. When we performed unsupervised clustering analysis, we found evidence of a high and low methylator subgroup within the Barrett's cases and also within the cancer cases. For example, in the Barrett's cases, 4 out of the 28 cases we looked at, or 14%, were low methylators, with the rest being high methylators. And among the cancer cases, 7 out of the 29, or 24%, were low methylators. When we looked at the ages of the low and high methylators, we found that there were no statistically significant differences, which is important since we know that methylation of some genes can increase with age. When we do moderated t-testing among the high and low methylator subgroups, we come up with a list of genes that is able to differentiate them. Thus far, we have 15 CpGs from 15 genes that distinguish the high and low methylators in Barrett's, and 74 CpGs that distinguish the low and high methylators in cancer. We're now in the process of validating our results using bisulfite sequencing of those CpGs of interest from the array. We'd also like to further correlate the histopathological data with the methylation status in these cases. It doesn't appear that age and methylation are correlated, but what about gender, length of Barrett's, stage of cancer, and that sort of thing? So in summary, We've done comprehensive DNA profiling and seen unique methylation signatures in squamous esophagus, Barrett's with dysplasia, and esophageal adenocarcinoma. And when we examine the Barrett's cases and cancer cases more closely, we find evidence of a high and low methylator group within each, which I think is the first time this has been shown. We hope that additional validation of the CpG sites that distinguish Barrett's from high-grade dysplasia and cancer might lead to the discovery of useful biomarkers with clinical applications. So with that, I'd like to thank you for your attention and for your interest in our work.